A recurring concept in statistics that underlies everything that we do is distinguishing between numerical and categorical variables. The observations that we collect on numerical variables are fundamentally different than what we collect on categorical variables. This difference impacts the choices we make in describing our data and using our data in making inferences. The definitions that are in the textbook are very clear and succinct. It seems like this would be an easy distinction. However, the word usually causes lots of problems, even for non-novices. An example of a categorical variable that might be reported in numbers would be the year in high school. Instead of recording freshman, sophomore, junior, or senior, it might be recorded as 1, 2, 3, or 4, perhaps even as 9, 10, 11, or 12 for the grade level. You may have seen a survey that asked you to pick a category for your age, 18 to 26, 27 to 35, etc. In both of these examples, the list of raw data would appear as a bunch of numbers when they were actually collected as categorical data. It takes discernment to keep from being fooled. Knowing how the data was collected helps to determine the type of data you actually have. Numerical variables will require that something be counted or measured. Categorical variables will require a description of a quality or choosing a group. Here are some example research questions that lead to different types of data. Here's what some of the data might look like in each case. You may still be thinking that it is all a matter of semantics. Not so. All of the subsequent description or analysis of your data will only be useful if the appropriate type of display or calculation is done. Let's review the sorts of displays and calculations appropriate for the different types of data. In either case, the data can be summarized by the creation of a table. Numerical data is compacted into classes so that the table doesn't end up with many rows having only a single item on each row, which isn't much of a summary. If we weigh passenger luggage to the tenth of a pound, 39.6 pounds and 39.8 pounds would be separate lines of a table unless we create classes, sometimes called bins, such as 39.0 and 39.9 pounds. Frequency means the count of items in the category or class, but that might be turned into a relative frequency, a decimal, or reported as a percentage. I'll illustrate the difference between a bar chart and a histogram on the next couple of slides. You can tell them apart by looking for the gaps between the bars and columns. Histograms do not have gaps. Pie charts are the trickiest. They are best used when there are very few categories, like the year in high school. You would not want to make a pie chart based on months of the year. Too many slices for a good visual comparison. You also don't want to make pie charts anytime there is a category with a frequency of 0, which wouldn't get represented at all. There are plenty of published examples of pie charts created using classes of numerical data, but it always makes statisticians grind their teeth. You can convey numerical information this way, but there are so many better choices. Why would you? Stem plots are wonderful for two-digit data, like ages or test scores, because the stems represent the tens digit and the leaves represent the digit in the ones place. They allow you to compact your list of raw data without losing the exact values. Dot plots also preserve all of the raw data while illustrating center and spread of the data set without any calculations. Finally, we can display numerical data with a box plot. Constructing a box plot requires some calculations first so that the data set is divided into quarters. Now let's look at each of these ideas. Here's some categorical data that I actually collected from a class. It's already summarized into a table and a couple of displays created from that table. Here are variations on those displays. Unlike the bar chart, there is no gap between the columns in this histogram. The shape changes some when I narrowed the width of the classes. It is something of an art exercise to decide on the right size for the classes. The stem plot also allows you to visualize shape and spread of the data, though you are forced into classes of the width of 10. This display could work with data that has tenths, like 5.2 and 7.5. With very clear definitions, the stems and leaves can represent other values. SAT scores on a single portion are always 3 digits, but also always end in 0, which could be ignored for creating a stem plot. If this dot plot had a clear scale, we could relist the raw data. We can see how very right skewed the distribution of this data is and make a guess at the mean being somewhere close to 25. The 5 milestones for creating a box plot are measures of relative location, describing how to divide up the data into 4 sections that contain the same number of observations between the milestones. This is a comparison of how numerical data could be displayed. A smoothed curve version of the histogram in a box plot. It is also a comparison of shape to the relative location milestones, the quartiles, and measures of center, how they relate to one another. Note that there are still 25% of the data between the milestones, even when they don't have the same area because the distribution is skewed. Just for good measure, here's a quick review of the notation used throughout the term.